All right, today we're going to dive into a deceptively simple rule from the early days of quantum theory. It's an idea that, honestly, is just beautiful. It explains why our universe, when you get right down to it, isn't smooth and continuous, but instead comes in these discrete, lumpy packets. I mean, really think about that for a second. In our world, the world we see, everything seems smooth. A car can go any speed, a ball can roll any distance. But what if that's just an illusion, an artifact of our large scale? What if, on the most fundamental level, particles are only allowed to have certain energies, certain momenta, certain motions? That's the core mystery we're going to start unraveling today. So, to wrap our heads around this, we're not going to start with a bunch of heavy mathematics. No, we're going to start with something way more familiar. We're going to start with a musical instrument. The first piece of the puzzle comes from Louis de Broglie, who came up with this really wild idea. He proposed that everything, and I mean everything, from a tiny electron to you and me, has a wave nature. The wavelength of this matter wave is directly connected to its momentum. And this isn't just some weird, quirky idea. It is the absolute key to this whole thing. Okay, so back to the guitar. When you pluck a string, only certain notes ring out, right? Those are the standing waves, where the wave fits perfectly from end to end. Any other vibration just kind of fizzles out. Well, believe it or not, the same exact thing happens to a particle that's trapped in some space. For its matter wave to be stable and not just cancel itself out, it has to fit, it has to resonate. And because that wavelength is locked to its momentum, this immediately forces the particle's momentum into specific, discrete, allowed values. And this is that resonance condition, just written down in the language of math. The equation you see, phi p dx equals nh, is the heart of it. That integral sign with a little circle, it's just a fancy way of saying add up the momentum over one complete round trip. So for a particle bouncing back and forth, this rule demands that its wave has to line up perfectly with itself after each cycle. And that can only happen if the total action is a whole number, n, times Planck's constant, h. That's a powerful start for sure. But to really see the full, glorious picture, we need to upgrade our viewpoint. We have to move beyond just thinking about paths through space and into a more abstract, but way more powerful landscape. Yeah, the particle in a box model is great and all, but what about more realistic things? A pendulum swinging or an atom vibrating in a molecule? Its momentum is always changing. It's speeding up, slowing down. How on earth do you apply a resonance condition to that? This is where we introduce the real stage of mechanics, phase space. It's a game changer. Instead of just tracking a particle's position, we track its position and its momentum at the same time. For a periodic system, like a harmonic oscillator, its path in this space isn't a line. It's a beautiful, closed loop, an ellipse. And this totally changes the question. We're no longer interested in the length of the path. We care about the area that the orbit encloses. And there it is, the big aha moment. This is the profound geometric insight. Quantization isn't just about fitting waves along a line. It's about geometry. It's about area. The allowed, stable states of a system are only those whose orbits in this abstract phase space enclose very specific, discrete amounts of area. And here is the rule, in its full glory. This is the Bohr-Sommerfeld quantization condition. That integral you see on the left, what we call the action, it is the area of the orbit in phase space. And the rule says this area can't be just anything. It has to come in integer chunks of Planck's constant, h. The entire structure of the atomic world, all the allowed energy levels, it all stems from this one elegant geometric rule. Okay, so this picture is almost perfect, but there's one more subtle, really beautiful little wrinkle we need to add. It's a correction that actually makes the model even more powerful and tells us something deep about what these quantum waves are doing. This correction happens at very specific places that we call the classical turning points. It's just what it sounds like. It's the spot where an oscillator, for example, reaches its farthest point, stops for just an instant, and turns back around. Let's go back to our wave analogy. Imagine sending a wave down a rope that's tied to a wall. When the wave hits the wall, it flips upside down, right? It undergoes a phase shift. Well, the de Broglie wave of a particle does the exact same thing when it bounces off these turning points. And our resonance condition has to account for these little extra shifts. For a system like a harmonic oscillator where there are two turning points, these reflections introduce a total phase shift. And this forces us to add a small but incredibly profound correction to our quantum number. It's not just n anymore, it's just a little bit more. So this gives us our final corrected rule. The area is quantized in units of n plus 1/2 times h. Now, that tiny plus 1/2 might not look like much, but it has absolutely monumental consequences. It means that even in its lowest possible energy state, when n is 0, the system's energy is not 0. It has a 0-point energy, a kind of constant, unquenchable quantum hum. This is one of the most fundamental predictions in all of quantum mechanics, and it falls right out of this model. Okay, so the rule works for oscillators. That's neat. But how far can we actually push this thing? Well, the answer is pretty astonishingly far. Now, let's just bust a huge misconception right now. It is so easy to think this rule is just a historical artifact, something that only applies to electrons and atoms. That could not be more wrong. This same basic rule explains the vibrations of molecules, what electrons do in powerful magnetic fields, how semiconductors actually work, and even why magnetic fields get trapped in discrete little packets inside superconductors. It even correctly predicts that if you drop a bunch of neutrons in a gravitational field, they'll bounce at discrete quantized heights. And here's maybe the biggest one of all. If you apply this rule to an electron moving through the repeating pattern of atoms in a crystal, it naturally predicts that there will be allowed bands of energy and forbidden gaps. And that band structure, that is, quite literally, the foundation of all modern electronics. The chip in your computer, the screen on your phone, it all comes back to this. But for all its incredible power, it is absolutely crucial to understand that this is not the final theory. It's a bridge, a powerful approximation, and like any approximation, it has a breaking point. You see, the rule depends on having those nice, clean, closed orbits in phase space. This happens in systems that are regular and predictable, what we call integrable. But in a chaotic system, think of a pinball machine, the trajectory never neatly repeats. It just explores the phase space erratically. There are no well-defined areas to quantize. And in that world of chaos, the beautiful simplicity of the Bohr-Sommerfeld condition it falls apart. And this brings us to the second big misconception we need to clear up. This is not the final word of quantum mechanics. It's what physicists call a semi-classical theory. It brilliantly connects the classical world of orbits and areas to the quantum world of discrete levels. It gives us an incredible, almost physical intuition for why things are the way they are. But it is not the complete, mathematically rigorous theory that came later. So, at the end of the day, what's the ultimate takeaway? What is the lasting legacy of this powerful, elegant idea? If you remember one thing from this, let it be this. Quantization isn't some bizarre, arbitrary rule that was just imposed on the universe. It is the inevitable, logical consequence of treating particles as waves that have to be self-consistent. It is nothing more and nothing less than a statement about resonance, about a kind of geometric harmony over a cycle. For a state to be stable and to exist, it simply has to be this way. And that leaves us with one final thought. The Bohr-Sommerfeld condition showed us how one of the deepest mysteries of the universe, its fundamental lumpiness, emerges from a simple and elegant principle. It really makes you wonder, what other profound rules about our reality are just sitting there, waiting for us, hiding in simple ideas of geometry and harmony?